Lab Guy here. Today we're going to review the NBTV BIG Televisor project, and I will bring you up to date as to where all of that is. It's very close to being a completed project. It is completely assembled and we're still debugging some servo issues, but we're almost there. In the last video I showed you the RGB illuminator module and how it worked and demonstrated it in operation. The video before that was the preparations for constructing an NBTV televisor based on a cathode ray tube. In that case we're using my antique Millen 90901 oscilloscope module as the foundation for that project. Today we're going to look at the current state of the NBTV BIG Televisor, do a deep dive into the schematic, going briefly over each circuit section and to what I expect it to do versus what it really does, and I will mention a circuit improvement which will make the system much friendlier to the NBTV community as a whole. So let's get on with that. Here is the NBTV BIG Televisor on the bench. This is the breadboard of circuitry for the servo system. It is rather complex looking, but it's not so bad overall in functionality. We have a 1/44 horsepower industrial motor, just because I have one. We have a high-powered motor drive amplifier, which we will examine in detail in the deep dive of the schematic. So let's get on with that right now. Starting at the video input jack on the upper left corner of the schematic, it is terminated in 75 ohms and goes into a LM1458 op-amp configured as a simple voltage follower. That then proceeds into an LM319 comparator, which its job is to separate the sync pulses from the video. These sync pulses are fed to Q1 and U3, an LM55 missing pulse detector circuit, and it finds the missing pulse in the sync stream. To review, in NBTV, frame sync is indicated by leaving out one of the line sync pulses. There are 32 lines in a picture, and once per frame at the beginning they leave out one of the line sync pulses. The missing pulse detector is set up in such a way as to detect that missing pulse. Coming out of pin 3 of the 555 timer, we invert the pulse and drive a 2N7000 FET, which is connected to a capacitor and a current source, producing a ramp generator. The ramp voltage generated here is in sync with the frame pulse of the video. It produces a ramp that lasts for one frame and goes from 0 volts to 5 volts approximately, and is buffered by U1B, another LM1458 op-amp configured as a voltage follower. The output of the voltage follower is applied to a DG211 CMOS switch, which is triggered by a pulse produced by the sync holes on the scanning disc. We'll come back to those, but let it be known that as the wheel rotates, once per rotation it produces a quick pulse that closes the DG211 switch. and the instantaneous voltage of the ramp is recorded on the 100 nanofarad capacitor. This is a sample and hold circuit. The capacitor is buffered by another LM1458 configured as a voltage follower so that it doesn't load the capacitor and doesn't discharge the sampled voltage. The output of that LM1458 is our phase error information, and it's applied to a potentiometer. Above that potentiometer is a second potentiometer. The top potentiometer sets the free running speed of the main motor. You'll see that the two resistors, the speed resistor and the phase resistor, form a summing node. The speed is a 10K resistor limiting current, and the phase resistor is 100K, so that its contribution is 1/10 as much current as the speed servo. The speed servo the speed setting should be dominant. These resistor values are prone to being changed as necessary to get the control range necessary. The output of the summing node of the two resistors goes through yet another voltage follower buffer. I buffer everything, which then goes to the motor drive amplifier. Before we go there, let's go back to the disk servo sync system. Disk sync is picked up by way of an LED shining through holes drilled around the rim of the NIPCOW disk. The light pulses are picked up by phototransistor PQ1, passed on to another missing pulse detector built with a 555 timer. On the rim of the disk, I drilled 32 holes, and then when I determined which hole is the correct point, I put black tape over it to create a missing pulse that tells us the phase of the wheel, and I've set that up in such a way that the wheel is already near where we want it to be in time with video. The missing pulse is called the disk tack pulse, and I pass that to a phase control one-shot. The range of this one-shot lets us vary the phase position of the pulse by plus or minus one rotation of the wheel, so that we can dial it around so that we are on the correct frame of video on the wheel to match the frame of video in the video stream. The second one-shot's job is to shorten the pulse to produce the snapshot effect on the sample and hold circuit that we covered previously. Looking closer at the first motor drive amplifier, you can see that it is essentially a power op-amp circuit with a gain of approximately 10 or 11. The input drive, MOT drive, comes in on the left side, is divided 5 to 1. It's actually divided 6 to 1 and fed to the op-amp, and the op-amp then drives the two output transistors. This circuit had a built-in bug in that the phase delay in the feedback was enough to cause it to oscillate at certain voltages. I decided not to fight with that so much, and I reviewed some of the circuits by the NBTV club, and they use simple voltage, not voltage followers, emitter followers to drive their motors, and so I formed a simplified version of my circuit using an op-amp and an emitter follower transistor to drive my motor. And that circuit is currently in test, and what I've discovered with it is my TIP29A transistor has a 1 amp current rating. The motor takes 650 milliamps when it is running at speed, and therefore that transistor is running extremely hot. The heat sink I have on it is too small, So I will be changing that transistor to a much higher powered transistor and putting a much larger heatsink. That's the plan for the motor driver amplifier. So that concludes the deep dive into the schematic of the servo system. One additional circuit will be added so that I bring my televisor in line with the rest of the NBTV community, in the sense that a DC restoration circuit will be added to the front end to cope with AC coupled video signals, which appear to be the standard in the industry rather than the exception. In my case, I always use DC restored signals for all of my video systems, and so I never need a DC restoration on an input. However, that's not the normal case in the NBTV club, so I will adapt this circuit so that it works properly with signals that have been recorded on sound cards, CD players, and tape recorders. That will be covered in a future video that I will make about signal termination, signal levels, and AC versus DC coupling. I will go into a deep dive on that subject. In my previous video, where I was demonstrating the illuminator module that I built, it was a color illuminator, and I do use the Aurora Designs WC1 world converter for all of my archaic test signals for all TV standards. This is a rare device. It is a hideously expensive device, and again, in the community in general, NBTV experimenters don't have the cash or the access to that device. A comment was put in, and I paraphrase, and it essentially said, "Where in the hell am I supposed to get RGB signals?" Good point. So a new NBTV project has been started here that I will elaborate on in a future video, but let me explain it to you now. It is a color NBTV frame store type signal generator. It uses memory chips to hold 256 still pictures in NBTV format, or up to 20.48 seconds of continuous video, and it will be built using a circuit very similar to the one I used in the Philocam sync generator. If you recall, in that project, prior to using the camera tube, to make sure that the video monitor I built and the sync generator were working, I put a frame memory on it with 8 stored pictures so we could debug the sync system and the television monitor before we tried to make the camera tube work. This reduced the severe number of unknowns at that time. Well, taking that same circuit, which held 8 pictures, and scaling it down to hold pictures, 2 kilobyte size pictures of NBTV, it will hold 256 frames of NBTV video. This project will have 3 memory chips with red, green, and blue video stored separately in each one, and the user will have the option of having either 256 still images, which is a lot, or a number of loops of video. If you store the frames of a video sequence, let's say you want to store 1 second, you would store 12 frames or 13 frames. You can't store, well, it's 12 and a half frames per second. So you'd put, for 1 second, you'd put 13 frames. So at any rate, I will put a microcontroller front end on that with a couple of rotary encoder, push-button style rotary encoders, and a 2-line LCD display, giving an interface similar to the world converter. in the sense that you can then use your selector knob to select one of your 256 stored pictures individually, or you can go in and program it, telling it that, let's say you have a 50 frame sequence of motion, and you can tell it that you have stored that from frame 205 to frame 255. And you can set the start and end points for a motion sequence. You can dial those into the motion playback system. And that can be assigned an index number as well, so that you can have a number of motion sequences, perhaps 16. So then when you dial through your picture selections, you can dial through a series of still pictures and a series of short motion sequences of your choice. Now, the downside of Rev 1 of this system will be that it is based on E² proms for the storage of the images, meaning that you'll need a device programmer and some software tools to put the images into the memory. When I build the device, and I will offer these for sale as kits, which will probably include a circuit board and the 4 programmed memory chips, and the rest would be up to the builder to accumulate the parts and put it together. But the device will put out a full monochrome NBTV signal, a fully compatible monochrome signal with sync, and simultaneous red, green, and blue video for driving color illuminators if one chooses to do so. I could also sell a stripped down kit which has 2 programmed devices and is monochrome only if you don't need the color. And the 4th program chip is a 2K memory chip which forms the timing state machine. So all of the video generation is handled by hardware, and the control is by way of a microcontroller. Now, for those who may be baffled that in a previous video I said that I don't like microcontrollers in video projects, that's not true. I don't like microcontrollers for generating video timing pulses directly. They have issues doing that, but using them as the control element to control video generating hardware, they're perfectly fine. In my job at Prime Image, a relatively well-known video company, back in the day, my job there in my final years was programming all of the front panel microprocessors in their equipment. So this is right up my alley. So anyways, that's enough about that. That's a future project which will be covered in a future video. So I hope that you've enjoyed this update today, and if you got anything out of it, you know what to do. And be sure that if you have friends that like this topical matter, to direct them to my channel to have a look to see if they like it. If you like it, you know what to do. You know which button to push and which bell to ring, because I don't want to elaborate on it. When I watch videos on YouTube and they go through that every time, it just grinds my gears. They think I'm stupid. Well, I respect my viewers. I know that you know how to subscribe and how to click a thumbs up or leave a comment. So, and how to make your projects work. And I hope you join me in building projects. Feel free to comment all you want. And so this concludes today's update. So until next time, Lab Guy out.